So now let's be quantitative with this curve. Before I showed you the qualitative features, let's talk about what happens when you're quantitative. When it comes to any acid-base neutralization, we have the formula, the molarity of the acid times the volume of the acid over the reaction coefficient of the acid equals the molarity of the base times the volume of the base over the reaction coefficient of the base. So if we know the reaction between the acid and the base, we can figure out VA and VB. Now, as I said in the previous video, this is a monoproduct acid, HA, plus a strong base such as sodium hydroxide, giving us water and a conjugate base. So in this case, it's going to be 1-to-1. So for any monoproduct titration, our formula reduces to this. Now, let's say we want to figure out the concentration of the acid based on this titration curve. Well, we have to be given 3 of the 4 variables to solve for the unknown. So since we wanted the concentration, the acid molarity of acid is going to be the unknown. Now, the nice thing is we can do this for both the weak acid and the strong acid case. We know the volume of the base at the equivalent. So this is where our VB is going to come from, is wherever this line is on the graph. The molarity of the base has to be given to us. This is typically where we're titrating a known width. So that's given. And the volume of the acid is typically given. So if we know the concentration of the base, and we know the volume is the equivalence point, and we know the volume of the acid, we can solve for the concentration of the unknown. And this is true for both the strong acid and the weak acid cases. So what about additional information? Well, there's one thing we can get off the weak acid that we can't get off the strong acid, and that's the dissociation constant, the equilibrium constant Ka. And that's because strong acids don't have that. They don't have a Ka associated with them. Their Kas are infinite. So how do we do that? Well, if all we are given is a titration curve, we have to rely on what's called the Henderson-Hasselbalch relationship. And the Henderson-Hasselbalch relationship says that the pH equals the pKa plus the log of the concentration of the conjugate base or the concentration of the acid at whatever point you're measuring. Now, this equation will only work if you're away from the starting point and the equivalence point. It becomes singular, meaning it doesn't work anymore. It becomes infinitely large by these points. But in principle, you can use this to calculate the pH from the pKa anywhere along the buffer region. Now, there is a major limitation of the Henderson-Hasselbalch relationship in that it relies on sufficiently concentrated acids and bases. So, if your concentration of HA is less than 0.1 molar, odds are the Henderson-Hasselbalch relationship will not work that well for you. The other thing is that it works better the closer and closer you get to the midpoint. So if you try to calculate the pH away from the midpoint, you're going to get more and more errors as you get further and further away from it. But here's the thing. If we know the volume of the base that we need to neutralize, we know half that volume is the volume at the midpoint. And at the midpoint, we have equal concentrations of conjugate base and parent acid. So this number becomes 1. The ratio of the concentrations become 1. And the logarithm of 1 is 0. So, at the midpoint, we have the relationship pH equals pKa. So if we know the pH at the midpoint, we know the pKa. And the pKa is just the negative log of the Ka, where the Ka is 10 to the minus pKa, or 10 to the minus pH. So this is the quantitative type of information we can extract off of these types of curves. We can get both the concentration by looking at the volume of the base at the equivalence point, as well as the pKa, the Ka, the ionization constant, by looking at the pH at the midpoint.